So third lecture out of this chapter 5. So we'll look at more examples of how to work with chiral molecules, and then look at this concept of diastereomers. Well, if you have more than one chiral center on a molecule. Okay, so first of all, let's just work a few problems. So maybe I ask you to draw a molecule. So draw R 3-fluorooctane, for example. So the easiest way to approach this, so let's draw 8 carbons. 1, 2, 3, come on. 4, 5, 6, 7, 8. And carbon 1, 2, 3 has a fluorine on it. So then, of course, if you recognize that carbon is chiral, so that's what the R pertains to. So if we want to show stereochemistry, then this third carbon is chiral. So if we want to clearly illustrate the chirality, we need to use a dash wedge structure so that we represent 3 dimensions. So when it's drawn in the line formula like this, without the wedges, it doesn't show 3 dimensions, so we don't know if this is R or S. But we do know on this carbon there's a hydrogen, there's a fluorine, there's an ethyl, and then there's this carbon chain. So let's go ahead and assign priorities. So fluorine's going to be 1, and hydrogen's going to be 4, and this carbon chain's 2, and the ethyl is 3. So on the wedge structure, this is going to be 3, and this is going to be 2. And we need this to end up to be R. So if we had 1 here and 4 here, then 1 to 2 to 3 would be counterclockwise. That would be S, and 4 would be in the dash wedge, so the arrow would stay. So if we put fluorine here and hydrogen here, then we have the S isomer, which is not what we want. We want the R isomer. So then we would have 1, 2. So then we know that the 4 needs to be here, so hydrogen needs to be there and fluorine needs to be there. Now we have the R isomer. All right, because this would be priority 1, 2, 3, 4. 1 to 2 to 3 would be counterclockwise, that would be S. Number 4 would be on a solid wedge, so we'd have to flip the arrow, so that would be the R isomer. Or you may have to go the opposite way. I give you the structure and you name the molecule. So chlorine's priority 1, this is going to be 2, 3, and 4. So 1 to 2 to 3 is counterclockwise, that would be S. 4 is in the solid wedge, so we got to flip the arrow. So this would be R. So now let's go back to our rules for naming. So which end do we number from, the left or the right? It's going to be the right, to keep the number scheme as low as possible. So we're going to have a 3-chloro and a 2-methyl and a 5-carbon chain, so pentane. And then we need the stereochemistry included. So the stereochemistry we said is R, so that goes at the front of the name in parentheses. So that molecule would be R 3-chloro 2-methylpentane. Or maybe I give you the molecule drawn like this. That's the Fischer projection already. So let's assign priorities. So bromine's 1, this is going to be 2, that's going to be 3, that's going to be 4. 1 to 2 to 3 is counterclockwise S. 4 is on the horizontal. So reverse the arrow. So this is the R isomer for the stereochemistry. Now in terms of the name, what's the longest carbon chain? Well, that would be 1, 2, 3, 4, 5. So this is a 6-carbon chain with a bromine at carbon number 3, and the stereochemistry is R. So this is R 3-bromo hexane. Right, hexane because it's a 6-carbon chain. The bromine's at carbon number 3, and we deduced that the stereochemistry was R already. Or if the molecule is given to you like this, and this is a little bit harder, or this is a lot harder to name this molecule. So first of all, if we find the longest carbon chain, so this is going to be carbon 1, that is carbon 2, and the circle is carbon 3 in the back, and then 4 and 5. So this is a pentane chain with a chlorine at carbon number 2. So this is 2-chloropentane. Now if we want to figure out what the stereochemistry is, so we basically have the molecule right that looks like that. So we got the methyl group here, got the chlorine on our left and the hydrogen. So from my perspective, yeah, methyl on top, hydrogen on the left, chlorine on the right, and in the back there's 2 hydrogens here and an ethyl group on the bottom. So what I find easiest to do when I have the molecule in a Newman projection, let's see, so that's Newman projection. I find it easiest to take the molecule and draw it as a wedge structure. So let's take this and draw it. So if that's the chlorine and we turned it like that, then the chlorine would be coming towards you. So it would be a solid wedge and this would be the dashed wedge. So from my perspective, I'm going to take the molecule and I'm going to turn it 90 degrees clockwise from my perspective. So if I turn this 90 degree clockwise, so I'm going to turn the molecule 90 degrees clockwise like that, so the chlorine is going to come out of the piece of paper and the hydrogen is going to go behind the paper or behind the computer screen. The methyl's up towards the top and the ethyl is going to be towards the bottom, and the back carbon's not chiral, so it doesn't really matter. It's just got 2 hydrogens on that carbon. So, but this carbon is chiral, so we need to get the stereochemistry right. Okay, so let's get the stereochemistry. So chlorine's 1, this pathway is 2, that's 3, hydrogen's 4. 1 to 2 to 3 is counterclockwise, counterclockwise is S. 4 is on the dashed line, so the arrow stays, so that arrow stays counterclockwise, so this is the S isomer. So this would be S2-chloropentane. Okay, so that's molecules with 1 chiral carbon. It gets more complex. What if you have 2 chiral carbons in the molecule? Well, let me go back to this right quick. So if we wanted to draw the enantiomer of this molecule, just as an example, if you want to draw the enantiomer, the easiest thing to do is flip 2 groups. So if we flip the chlorine and the hydrogen, so if this is S, then this is going to be R. And it didn't matter which 2 groups on that chiral carbon we flipped. We could have flipped the hydrogen and the methyl, or the chlorine and the methyl, or the hydrogen and the chlorine. Or if we have the molecule drawn as a dash wedge, and you want to draw the enantiomer, then all you have to do again is flip 2 groups. So if we take the hydrogen and the chlorine and flip their positions, then that would be the opposite stereochemistry. This would now be the R isomer. And these 2 molecules would be enantiomers of each other. If you only have 1 chiral carbon and 1 is R and 1 is S, those molecules are enantiomers, assuming that all of the atoms are attached in the same order and they're not constitutional isomers. So 1 chiral carbon, if 1 is R, 1 is S, they are non-superimposable mirror images, they are enantiomers. But the situation is more complex if you have 2 chiral carbons. So like this, we have 2 chiral carbons. So how many possible stereoisomers there are? The formula, let's see, it's 2 to the n power is the formula. So n is the number of chiral centers. So if there's 1 chiral center, like in this molecule, so 2 to the 1 equals 2, there's 2 possible stereoisomers. There's the R, or there's the S. But if there's 2 chiral carbons, then 2 to the 2 is 4, so there's 4 possible stereoisomers. What are those 4? Well, both chiral carbons could be R, or both chiral carbons could be S, or 1 could be R and 1 could be S. So example, maybe the one with bromine is R and the one with chlorine is S, or 1 could be S and 1 could be R. So maybe the one with bromine is S and the one with chlorine is R. So there's 4 possible combinations. If you had 3 chiral carbons, then 2 to the 3, so 2 times 2 is 4, times 2 is 8. There's 8 stereoisomers. You know, what are those 8? Well, 3 chiral carbons, they could be RRR. or they could be RRS, or they could be RSR, or they could be SRR. So you could have 3 R's or 2 R's and 1 S, and there's 3 combinations of that. Or you could have 1 R and 2 S, and there's 3 combinations of that. Or all 3 stereocenters could be S. So 8 possible stereoisomers. Okay, so let's take this one with 2 chiral carbons. So let's draw the 4 possible stereoisomers. And again, when it's drawn like that, it does not show 3 dimensions, so you have no idea if those carbons are R or S. If you want to know if they're R or S, you need to add wedges. So you need wedges so that you don't see 3 dimensions. So there's 4 possible stereoisomers, so let me draw 4 templates. Okay, so we could put the bromine on the solid wedge and the chlorine on the solid wedge. That would be 1 possible stereoisomer. So what's the stereochemistry here? So let's assign priorities. So on this carbon with bromine, that's 1. This pathway's 2, that pathway's 3, and that's 4. So 1 to 2 to 3 is clockwise, that's R. 4 is on the dash wedge, so it stays R. So this is R at that carbon. And now we do the one with chlorine independently. So chlorine is 1, that pathway is 2, that pathway is 3, that hydrogen's 4. So 1 to 2 to 3 is clockwise, that's R. 4 is on the solid dash wedge, so the arrow stays R. So this is the R-R isomer. Okay, so to create the others, just be systematic about it. So we could keep the bromine and hydrogen same, and we could flip the hydrogen and the chlorine. So we didn't do anything to this chiral carbon, so it is still R, but we changed 2 groups here, so that one is now S. I mean, it's easy to demonstrate. Just go through your sequence. 1, 2, 3. 1 to 2 to 3 is clockwise R. 4 is on the solid wedge. So you got to reverse the arrow. So that would be the S stereochemistry at that chiral carbon. So that's the RS isomer. Or if we go back to our original, we could have flipped the hydrogen and the bromine, and we could have kept the chlorine and the hydrogen the same. So what would be the stereochemistry here? Well, originally the carbon with bromine was R. We changed through groups, so it must be S now. And we didn't do anything to the carbon with the chlorine, so if it was R to begin with, it is still R. And then what's the other possibility would be to flip both. We could flip the H and the bromine, and the H and the chlorine. And so if it was RR to begin with, now it is SS. That would be the SS isomer. So that's your 4 possible stereoisomers. Okay, so now what is the relationship between these? Okay, so we got a molecule with 2 chiral carbons. Right, this carbon's got green, white, and red. And this carbon's got blue, green, and white. So both carbons have 4 different groups, so they're both chiral. Let's see. So if we take this molecule, so if we notice the blue, green, and white match on one carbon, but the other carbon, the greens match, but the red and whites don't match. So one chiral center is the same and one is different between the 2 molecules. So that was, so if we call this 1, 2, 3, and 4. So if I say that this is number 1, so this could be 2 or 3, because one chiral center is the same and one chiral center is different, right? So if you notice, so these molecules, let's see. So the back carbon, it's kind of hard to tell. I'm trying to get this right on the camera. I don't know if I can get the right angle. But you can build your molecules. The back carbon is a mirror image of each other, but the front carbon is not. And so these molecules are not mirror images, and these molecules are not superimposable. You can make one of the carbons match, but the other carbon doesn't match, right? If one of the atoms matches like the whites match here, the other two atoms don't match. So these two molecules are not mirror images, they are not superimposable, and so if they are not mirror images, and they are not superimposable, but all of the atoms are attached in the same order, so they're not constitutional isomers, so they only differ spatially, right? But they're not mirror images and they're not superimposable, so these are said to be then diastereomers of each other. And so let me grab the other model that I have built here. So let's see. Okay, so these two molecules, so I can make the green atoms here match and the blue atoms here match, but then the green and white here don't match, and on the other chiral carbon, the red and white don't match. So neither chiral carbon is the same, both are different. So this would be like comparing 1 and 4, where both chiral centers are different. So for these molecules, if we notice, so these molecules are mirror images of each other. So maybe that's possible to see, if I can find a better way to hold them. So those molecules, the front carbons are mirror images and the back carbons are mirror images. So these are mirror images, but they're not superimposable. So the relationship between these two molecules would be enantiomers. So to be enantiomers, every single chiral carbon has to be different. So for example, if you have the RR isomer, its enantiomer is SS. So these two are enantiomers. If you had an RS isomer, then its enantiomer would be S. If you had an RS, its enantiomer would be SR. So these two molecules would be enantiomers of each other because the carbon with bromine is R in one and it's S in the other. The carbon with chlorine in one is S and the carbon with chlorine in the other is R. So every single chiral carbon has to be opposite to be enantiomers. So if you had a molecule that was RRSR, its enantiomer would be SSRS. And anything else, they would be diastereomers, right? So if they differ in one chiral center, or more than one chiral center, but not all, but if not all of the chiral centers are opposite, then they are diastereomers of each other. So if we go back to this, for example, this is the enantiomer of that. So if we call this molecule 1, let's call this 1, 2, 3, 4, 5, 6, 7, 8. So molecule 1, every single molecule has one enantiomer. So molecules 1 enantiomer is number 8. Every single chiral carbon is flipped. If we compared 1 and 2, they're diastereomers. If we compared 1 and 3, they're diastereomers. 1 and 4, they're diastereomers. Right? 1 and 5, let's do it this way. 1 and 2, diastereomers. 1 and 3, diastereomers. 1 and 4, diastereomers. 1 and 5, diastereomers. 1 and 6, diastereomers. 1 and 7, diastereomers. 1 and 8, enantiomers. Every molecule only has one mirror image, right? You only have one mirror image. Your hand is chiral, it has one mirror image, right? So everything only has one mirror image, so any molecule that's chiral only has one enantiomer. But there's lots of pairs. If this molecule with 3 chiral carbons, there are lots of pairs of enantiomers. So for example, if we took, let's take number 5. What's the enantiomer of number 5? Well, if it's RSS, its enantiomer is SRR. So that would be number 6. So number 5 and number 6. Is that right? No, that is not right. The enantiomer would be number 7. Number 7, is that right? Is, oh my gosh, no, that is still not right. Let's try this, let's try again. So RSS, we're looking for SRR. That's number 4. So the enantiomer to number 5 is number 4. If we took number 3, number 3 is RSR. What is its mirror image? Its mirror image would be SRS, so that would be number 6. So number 3 and number 6 would be enantiomers of each other. Any other comparison, they would be diastereomers of each other. So, but you can't have diastereomers if you only have one chiral carbon. Right, because if the molecule's chiral carbon is R, and you had another molecule, then the only possibility is it to be, for the stereochemistry to be R, in which case they would be the same, or its stereochemistry to be S, in which case it's opposite, and so they would be enantiomers. So one thing that you'll have to do is I'll give you several molecules and ask you to compare them. And if the molecule only has one chiral carbon, and you're comparing two molecules, and I ask you what is the stereochemical relationship between them, the answer is never diastereomer, because to have diastereomers you have to have at least 2 chiral carbons. If you only have 1 chiral carbons, then the 2 molecules are either the same or they're enantiomers. If you have 2 chiral carbons, right, then the molecules could be enantiomers or they could be diastereomers of each other. But the only way to be enantiomers is every single chiral carbon is opposite. Anything else, they would be diastereomers. So, for example, let's just give you a couple of molecules with 2 chiral carbons. So OH, H, CH3, chlorine, H, CH2, CH3. So let's take that molecule. And that molecule. So are these 2 molecules the same? So we'll call this A and B. So if we take A and B, they're either the same, they're enantiomers, or they're diastereomers. And which is it? I have no idea until we figure this out. So let's assign stereochemistry. So for this first carbon, that's priority 1. Down below is 2, methyl group is 3, hydrogen is 4. So 1 to 2 to 3 is clockwise, that would be R. 4 is horizontal, so we have to reverse the direction, so it's S. Okay, so this carbon with the OH is S. And now the carbon below is also chiral. So chlorine is priority 1, hydrogen is going to be 4. Going up to the top is going to be 2, and down toward the bottom is number 3. So 1 to 2 to 3 is counterclockwise, that is S. 4 is horizontal, so we got to flip the direction, so it's R. So this is the SR isomer. Okay, how about the dash wedge structure? So this is 1, this is 2, this is 3, that's 4. 1 to 2 to 3 is clockwise, that's R. 4 is on the dashed line, so the arrow stays. So this is R at the carbon with the OH. And the carbon with the chlorine, that's priority 1, that's priority 2, that's priority 3, that's 4. 1 to 2 to 3 is clockwise, so that would be R. 4 is on the dashed line, so the arrow stays R. So this is the R isomer. This is an SR isomer, so A and B would be diastereomers of each other. The only way, so if A is SR, then the only way to be the same would be B would have to be SR. And specifically the carbon with OH would have to be S and the carbon with the Cl would have to be R. Then they would be the same. To be enantiomers, this would have to be the RS isomer. B would have to be where the carbon with the OH would have to be R and the carbon with the chlorine would have to be S, so that it was opposite of A. So it's not the same, it's not opposite, therefore they are diastereomers. And that's just another form of spatial isomer. That's not mirror images and not superimposable. So if we compare A and B, diastereomers have different physical properties. So diastereomers have different physical properties. So A and B, if they are liquids, they could have different boiling points. If they are solids, they could have different solubilities. So diastereomers, therefore, can be easy to separate, unlike enantiomers, which have the same physical properties. And diastereomers also have different chemical reactivity. And it doesn't matter if the environment is chiral or non-chiral. They can react differently. They don't have to react differently, but they can. And usually in a chiral environment they would. So if A and B was a pharmaceutical agent, they can have different biological activity. So you would have to separate them, and you would have to test the biological activity of both of them separately to make sure that one is not toxic. Okay, if neither is toxic, then you can administer them together, and and a pharmaceutical company doesn't have to invest the time and money to separate them. If they are physiologically different, then obviously you have to separate them and administer only the one that has useful physiological activity. Okay, so another aspect here. If you have two chiral carbons, so let's draw a Fischer projection of the molecule. So to do this, you do each one separately from each other. So let's draw a Fischer projection of the top one. So since the wedge is pointing towards the top, then you want to be laying at the top of your paper looking down on it on your side and draw what you see. So in this case the methyl would be towards your head, and the chlorine would be on my left hand, and the hydrogen, which is behind the page, would be on my right hand. And then for the other chiral carbon, then you view it differently. So you don't keep the same perspective, because in a Fischer projection the horizontal must come towards you, right? So you must view it so that the horizontal is coming towards you. So if you look at the carbon with bromine from the top, those wedges are going away from you, which would not be a Fischer projection. So you have to come down here to the bottom and view this from the bottom. So if you're laying on the bottom of the piece of paper looking up, then you would no, we can't do that, because if we do that, then that would put the methyl towards your head. But we have already defined that this is going to be the carbon with bromine on it, and we have already defined that this is going to be on top. So we need to look not from that perspective, we need to look from this perspective, where the carbon with the chlorine is on the top towards your head, and then that will put the methyl group on the bottom towards your feet. Okay, so if we're laying at it like that with our feet towards the right, then the bromine's going to be on your right hand, and the hydrogen's going to be on your left hand. So that would be a Fischer projection. Okay, so if we name this molecule, so first of all, let's just name it without worrying about stereochemistry first. So 1, 2, 3, 4. So we would have 2 bromo, 3 chloro, butane. But this is a chiral molecule, and the chirality is clearly shown, so we need to indicate the stereochemistry in the name. So now we need to assign stereochemistry at each chiral carbon. So bromine's priority 1, that's number 2, methyl group is number 3, hydrogen's 4. 1 to 2 to 3 is clockwise, that's R. 4 is on the dashed line, so the arrow stays clockwise. So carbon number 2 is R, so this is 2R. And then we need to get the stereochemistry of the carbon with chlorine. So chlorine is 1, And this pathway is going to be 2, methyl group is going to be 3, and hydrogen is going to be 4. So 1 to 2 to 3 is clockwise, so that carbon is R also. So this will be 2R, 3R, 2-bromo, 3-chlorobutane. So the stereochemistry always comes in the name at the front. And if you have more than one chiral center, you have to indicate the stereochemistry of every single carbon. And you would put the number to indicate what the chirality is at that specific carbon. Okay, so if we had this molecule, for example, so if I just flip the stereochemistry at both chiral centers, then this is now 2s, 3s, 2-bromo, 3-chlorobutane. And if I only flipped one, so let's say we keep this the same, but we compared to here. So we keep the chlorine the same, but we flip the bromine. Then this molecule would be, okay, so it was 2R, so now it's 2S, and 3 is still R, right? And the other possible stereoisomer would have been, we had that one flipped, and we kept that the same, so then this would have been the 2R, 3S, 2-bromo, 3-chlorobutane. So that would be the 4 different stereoisomers. And the 2 that would be, so what would be enantiomers? If this is A, B, C, and D, then the 2R, 3R, so A and B would be enantiomers. C and D are opposite stereochemistry, would be enantiomers in any other comparison. So A compared to C, A compared to D would equal diastereomers. B compared to A is enantiomers, compared to C is diastereomers. B compared to D is diastereomers. And I think that's all of the comparisons, right? Okay, so hopefully that makes sense.